Okay. So we're going to be solving systems of equations. But there's three different scenarios. So let me show you what the idea is visually. So let's say you have some random line like this. Okay. Oops. And we have another one. You can see that they never intersect because these are parallel lines. So whenever you have parallel lines and they ask you to solve the system, you would say no solution. Okay, because they don't intersect. Now, let's say they were make it simple. You have two lines intersecting at a single point. When that happens, your system has a unique solution. It's just one right here. Okay. Now, if they are on top of each other, let's say they're some multiple of the original. Oops. When they're basically the same line or written differently, but the same. They intersect everywhere, so you're going to have infinite solutions. Okay. So those are the three scenarios. You have a finite solution, uh, no solution, and infinite solutions. Okay, so on this first question, this question one on the homework. Let me show you what it looks like first. Here's the question one. So they want to know, okay, given this system, in other words, two equations, is A, B, or C, etc., solutions to the system. Okay. Now, if they are parallel lines, then none of them are solutions, right? If there is a unique solution, then they're going to intersect one time. So only one of these would actually work, right? So once you find one of them or find the answer, only one can be true and the rest would be no. And if they're on top of each other, then you have infinite solutions. So more than one could be possible from the list. Okay. So let me put the grapher back on. So we're going to use our Desmos here to graph it. Let's keep it simple for now. And then I'll show you how to solve it algebraically in a minute, but let's just graph it and understand what is a solution to a system. So these two are a system. It looks like they are parallel. So since they're parallel, they will never intersect anywhere. So this is no solution. So in your homework, this particular problem, since they never intersected, well, they all have to they all have to be no, right? Let's see. So what they do is they say, you know what? Plug in the point. This is part A. Plug in this point into equation one and equation two and see what happens. Now, you need to get a true statement, meaning equality on both sides. Here you get a false statement. -3 is not equal to 17. So that means when they plugged in this into the first equation, it didn't work. It's not a solution. So if one of them doesn't work, then not a solution. So here's all the work that you would show, but if you graph them, you can tell right away. So what you do is you take let's look at part A, 2 and -3, right? It's right there. Then plug in 2, -3 into this first one, the top equation, the second equation. And notice that here we get what we saw earlier, -3 go to 17 and 30 go to -10. So like, no, not a solution to the system. So basically, the only way it's a solution to the system is if it satisfies both at the same time. See how in this one, they plug this guy in and this guy, and they got a yes, and another yes. Although it looks like I made a typo. I put +10 on the grapher. Because we said there was no solution, but check it out, there's two. And remember the three scenarios we said they can either be one solution, no solution, or infinite solution. So the fact that there's two means that this is the infinite case. Okay, let's go back to the grapher because I clearly messed up. This should be a minus. Oh, check it out. Now that I fixed it, they're on top of each other. So they intersect infinite many times all over. So infinite solutions. So the fact that two worked was a big clue that this is going to be the case. But to do it by hand, you plug in the points that they give you and see if you get a true statement. If you get 5 equals 7, then that's false, not a solution. If you get 7 equals 7, well, cool. That answer works. Now try it on the other equation. That's all you got to do for these. Are there any questions on this first problem? Okay, this is number 2. This one says to graph it, so we might as well just do what we just did one more time. So it says graph the system of equations. Okay. Again, it looks like, oh man, that's another infinite case. They're all on top of each other. All right, well, we just gotta graph this on the problem. Okay, so here's question 2. So click your line stuff. Pick your first point for equation 1. That's 0, 2 for your intercept. Use your slope. Go up 1 over 2. That should be one line. Okay, if you plug in 0 for the x, or let's see, for the y, you'd get x equal -4. So this has a point there. Did I mess up again? Let me see. No. Yeah, that doesn't make sense because they're supposed to be the same. Double check. 0, 2 of 1 over 2. The other one should be, if you plug in 0 for y, Did get -4. Oh, yeah, that's what I did it backwards. I see. There we go. Place the point. Strange. Okay, whatever. My grapher's being weird. Anyway, they're both on top of each other. You have infinite solutions because they're on top. And that's it. Graph them on Desmos or by hand or on here and find your what case you have. Okay. This is the infinite case. All right, so same stuff. Let's move on to something different. Any questions on number two? So yeah, this should be familiar. This is technically review, but if you don't remember this, that's okay. Let's move on to elimination or substitution. Okay, so this is an algebraic technique, so we'll do this on paper. This is number three. Okay, so it's use. This is number. Let me write down the section. Already forgot. This is 9.1 systems of linear equations. Okay, so number three. So the first two we did by graphing. You can technically use graphing anytime, but if they ask to do it algebraically, then we gotta. To use substitution to solve the system. Let's see if I can make that less blurry. Okay. Here is the system. So we solved by graphing. Now we're solving by a substitution. All right, so um, we're going to plug in equation 2 into 1. So plug in into equation 1. So we're going to get 2x minus 3 times 3x minus 8 equals 17. So now notice everything's in terms of x. There's no more y's because I did the substitution. So now you can solve for x. And that will give you one of the points for the solution to the system. Okay. If there, if you get a false statement while you're solving, then you have no solution. If you get a true statement, but all the variables cancel, like 5 equals 5, then infinite solutions. If you get a number, then you have the unique solution case. So let's find out. Okay, combine like terms. 2 minus 9 is 7, -7. 24 is still there, so I'm gonna move this 24 over there by subtraction. So -7 equals. 1 second, sorry. Someone's trying to join the room. Oh, there it is. Okay. So 17 minus 24, that's gonna be what? -7. Divide both sides by -7. So now we have the x variable. So now plug this into, so let me write instructions here. Once you find one of the variables, plug it into equation 1 or 2, doesn't matter which, and solve for the other variable. So here we go. I'm using equation 2. 3 times 1 minus 8, that's going to be 3 minus 8, which is -5. So we have both equations now. Okay, sorry. So the solution to the system is going to be a point. 1, -5 is a solution to the system. Okay, so any questions about the algebra steps? Does this make sense? I'm going to show you the graph so you can get another idea too. All right, there's my two equations. Remember, a solution to a system is a point where they intersect. If there's a unique solution, right? We solved for the x and we got 1, right? And then we plugged that in and got -5. So we use algebra and substitution to find the intersection point here. If there was no solution, then they would be parallel, or if there was infinite, they'd be on top of each other. So this is a unique solution case. Is there any questions on problem 3? Alrighty. Let's pick another one then. Okay, so the next equation or next system we're going to solve using elimination instead of substitution. For substitution, it's not always going to be solved for you automatically. You may have to isolate x or y in either equation and then just plug it into the other equation. So this one was already solved for, so it's easy to just show you how it works. But sometimes you might have to do an extra step, like maybe move something over here. Okay. Solve the system. Remember, you can always graph it and check your work or check what's going on first if you want. But we got to show our work for when they ask for a specific thing. Okay. Okay, so equation one and two. So the idea, remember, they're both equations, so you can do whatever you want to both sides for the most part. So if you want to eliminate a variable, you want to add them together. So in order to add them together, you gotta choose a variable to eliminate, and then make sure that they're the exact same number but opposite signs. So I'm gonna choose to eliminate x because it's pretty close to a six, right? If I cut this in half, I'll be good. Seven and eight, I'm like, it looks harder to make these the same. It's kind of like it's kind of like doing least con multiple. Okay. Okay, so what I'm gonna do is divide equation two by -2. So there, I made a new equation two, still equation two. So the goal is to change 12x into negative 6x. That's why I did this. All right. But now I can add them together. Shoot, lost my. Hmm. Okay, the first one's negative 4. This is negative 4 as well. Okay. There we go. So this is where the elimination begins. So add these straight across. 6 minus 6 is 0. That's why we did this, to get rid of one variable. 7 minus 4 is a 3. Negative 4 minus 4, negative 8. Okay, now divide both sides by, let me double check here. I think I messed something up. Oh yeah, shoot. This is supposed to be a 16 right here. This changes to a 16 just so the numbers are prettier. Should be equal to 16. I mean, it doesn't have to be. It's just to make this example easier. That's all. Okay. So this would be 16. Let me fix this real quick. Nothing really, no, the work doesn't change. It's just, you know, just changing a number. So negative 4 minus 8 is a negative 12. So I did that all in order to get a pretty number. That's the only reason. Okay, so now divide both sides by 3. And we get y. So y is equal to negative 4. So we have one variable. So we add equations together to cancel one of the variables. Then you solve for the other one here. Once you have one of them, just plug this into either equation. So now plug in y equals negative 4 into 1 or equation 2. Okay, so I'm gonna plug it into 1, I guess. Hmm. Yeah, it doesn't matter. So 6x plus 7 times negative 4, plug it into y. Okay, let's add 28 to both sides. I'm running out of space here. That'll give us 24, which means that x is equal to 4. To divide both sides by 6. Let's skip a minor step. So the solution to the system is a unique point 4 comma negative 4. So we use elimination to get rid of one variable. Just like on the substitution, we plug in a variable in order to get it down to one variable. And then we solve for the remaining variable. Okay. So that's the goal. Get it down to one, solve for it, then plug that into either equation. Once you have that, you're good. Now let's graph it for fun. Let's see. Okay. Equation one was this guy. There's the point that we solved for negative 4. Intersect one time, unique solution. Any questions on number 4? Okay. I think that's almost all the cases on this homework. Let me see what else we can check out real quick. Here, let me show you some terminology. All right. So notice system A is those two equations and they're parallel to each other. So they never intersect, they just keep going, right? Forever. So we call this a inconsistent system, meaning no solution. So you'd say no solution for part A or for system A, inconsistent because they never intersect. System B is the unique solution case because you see the single point here, right, of intersection. So this is a consistent independent system right here. If they're on top of each other, then they're considered dependent on each other. So consistent dependent system. And then we said if they're on top of each other, there's infinite. If there's one intersection point, unique. If they never intersect, well, no solution. Okay. Oh, let's move on to something else. 1 second. Let me